All right. Good morning, good afternoon, and good evening, everyone. Thanks for joining this session of the Exotherm webinar series. So, welcome to today's topic around future-proofing critical electrical assets through predictive maintenance using CTM, continuous thermal monitoring. My name is Thomas Schmidtjen, and I'm running Exotherm's activities in Europe, Middle East, and Africa. And I'm happy to be joined today by our Chief Technology Officer, John Hope. Welcome, John.
Thank you, Thomas.
Very good. This webinar series will continue throughout the year 2024, with additional sessions shedding some light around the topic from different angles, such as understanding the broad technical landscape around different continuous thermal monitoring solutions out there. Then a topic around the importance of temperature. Why does delta T actually make the difference, and how do load-related alarms change the world for end users and operators in running more resilient and safe operations? And then finally, taking the topic into different applications examples across the power distribution train, maximizing resilience for electrical assets, and how continuous thermal monitoring is becoming a standard for predictive maintenance. So, electrical power, everyone, is playing a vital role in supplying the global energy demand. And trends like urbanization, e-mobility, renewables and decentralized generation, data and digitalization, process electrification, and so on, is becoming ever more relevant. Electrification is critical for improving the quality of life of people across the world. It's the lifeblood of modern society. And on that journey, and contributing and addressing the energy trilemma around availability, affordability, and sustainability, it's all about running more resilient operations. A reliable power supply with less interruptions, and about keeping people safe. And with the trends around remote operations, the demand substation, the electric mine, digital refineries, or the autonomous data center, it's all about the use of smart insights through data-driven analytics, and that's exactly where, in power distribution infrastructure, continuous thermal monitoring, CTM, comes in and is playing a pivotal role. To give you an example, here's 3 different companies who've been facing massive hits based on power outages. For example, Apple has had a loss of over $25 million due to a 12-hour power outage, taking the App Store, taking iTunes, and so on down. The other example is Meta and Facebook, who faced a hit of over $90 million due to a 14-hour power outage. And finally, the example of Delta Airlines, who, due to a 5-hour disruption of the power distribution system, had over 2,000 flights cancelled, with tens of thousands of people stranded in airports and in transit, with an estimated cost to the company of over $150 million. So just with putting things into perspective, this session around continuous thermal monitoring, fundamentals and characteristics, I'd like to hand over to John for taking us through some of the fundamentals. John.
Thank you very much, Thomas. Thank you. So where I'd like to start is, as Thomas says, going to the fundamentals, start at the basics of where do we need CTM? Where would we actually place CTM as an end user, as a customer? Where would you put the equipment? Well, we'll start at the very start of the cycle, the generation, the power source. We can have CTM within generator systems, within solar farms or wind farms. There is suitable voltage for this. If we look actually to the grid, it generally is too high a voltage to start putting sensors in because of clearance levels and other areas. But that generator, solar farm, wind area is ideal for CTM, adding that continuous monitoring. That then moves into the transformers, and these can be dry type, they could be oil filled, and they could be step down, step up. Again, that's an ideal point for CTM. Put the monitoring there. We then move round the cycle into the medium voltage switchboards. Again, put them in the boards. And medium, the same as low, which we'll come on to a second, it's critical joints. They're the areas that we need to monitor. Now, what do we mean by critical joints? It's the site-made connections. So it's a connection that's physically made on a site, cables or bus duct systems feeding into a board, and the cables on a bus duct system feeding out. It's the connection made by the electrical contractor. That was seen over the years, that's been the weaker area. And then the shipping split, so where a board is actually brought together and assembled on site. Again, that seems to be, it's a weaker area. It's not all internal connections, because they're factory made. They're torqued, they're checked, they're quality checked, they're checked again. They're not the ones that fail. It's the site-made connections. Again, between here, we've got some transformers. They can be MV to LV or LV to low voltage. Again, we see issues, especially on the dry type, the resin core. It's an ideal position to put continuous monitoring. We then move round, and if it's into a data center market, we'll see UPS systems, so that uninterruptible power supply. And again, ideal candidate for installing CTM. Generally not on the individual battery banks, but the main battery cables into the unit, because for a battery system, there are battery monitoring packages and software out there already that are specialised. That's not what the CTM's there for. And then finally, we're coming down to we're saying here, the power supply to the server racks, or it could just be distribution boards around the facility. Again, ideal candidate for CTM. So, why does power fail? Well, I think as we can see from this image here, it's quite catastrophic. It's a mess. And the most common cause of a failure in any switchboard, any electrical system, which remains undetected, is a loose connection. The quote at the bottom there from NETA, a major insurance carrier estimates 35 to 40% of all major electrical failures are due to loose or faulty connections. So it's that faulty connection. It makes a mess. It causes you an outage. And it's not just the fact that the cable's failed. A solenoid, a contactor's failed, or a breaker's. It's the other damage that it causes at the same time. So at the moment, let's have a look at key issues with what we're saying is the current approach. And the current approach, there's been nothing wrong with it. It's using thermal imaging. And as ever, it was the best technology available at the time. But now we've evolved. We've moved on. Thermal imaging. Inspection frequency. It's less than 1% of the available uptime of that equipment. You're taking a snapshot. A very, very small moment in time. It could be seconds of the gear is operating. You've got the other thousands, tens of thousands of seconds the rest of the year. You're not checking it. It's almost like saying, if I had a tablet and some medicine, pills, And we said, you can have a pill and this will stop you becoming sick. But tell me, which day of the year do you want me to give you that medicine? Which day do you want that pill? You don't know. Or, you know what? Take one of these pills every single day. You'll not become ill. That's the difference between the two. So, inspection frequency, as I said, less than 1% of the uptime of that key. Direct line of sight. You're outside the equipment. You're trying to look at something inside, a connection inside the point. You've got issues of obstacles. There could be other cables in the way, other breakers. The connections are right at the back, right to the rear part of the board. You can't see them. If a joint is actually booted, so it's got the insulated boot around it, even with a camera, you can't thermal image. There's an air pocket. It's impossible. And that temperature measurement, it requires correlating. It's correlating to load, to other conditions. So the inspection results can be very different from one thermography to the next. They could have a totally different reading. And we mentioned the very last point there, it's additional maintenance. Windows within a piece of gear, although they're great pieces of kit and they work with the cameras, they do need maintenance. They need gasket changing. They themselves need replacing every so many years. You need to make sure the screws are tight, that they're clean. And you have to calibrate the camera to the window every time you want to use it. So it was great technology, but we've evolved. We're moving on. If we look now over the years, and I quite frighteningly remember when I first started 40 years ago, yes, it was reactive maintenance. It's where it all started. Everybody reacted to a problem. If a piece of equipment failed, a switchboard failed, a connection was failing, you reacted, but it was too late. Generally, you were too late. You were having to fix as it was broken. This then evolved and moved on a few years later and became periodic maintenance. There was ticketing systems and software packages to print out every 3 months, every 6 months, you must carry out this maintenance. It worked, sort of worked, but the problem was it became, for an end user, it became very expensive for you because you were having to carry out maintenance whether that piece of equipment needed it or not. You were having to carry spares. You were having to replace components. At times you were taking good components out to put another good component in. So it was expensive to an end user. This then tried to become proactive and try to mingle the two together. And it tried to add in eliminating that defect as soon as possible when you detected it. But again, it was not perfect. It was never going to be perfect. So we've then evolved further. We've said next is predictive. Well, if you want to predict, you've got to have data. And there's no point having a snapshot of data that tells you it was good 7 months ago. You need to know 24/7. So continuous thermal monitoring will give you that data. Will give you the health of your equipment 24/7. We're helping you predict. You've got data. You can analyze that data. We can start to use artificial intelligence, which is coming whether we like it or not. And for engineers moving forward, it's going to be a great asset because you'll be able to compare season to season, ambient conditions to ambient conditions, different humidities, different processes running in your environment, your data center, your refinery, your mine. Is anything causing a problem with the equipment? All this data will help. and will help you predict when you need to carry out the maintenance. So it helps it become more cost efficient, very cost efficient. So CTM, continuous monitoring, it's closing the performance gap. We know thermography is less than 1% of that uptime. It's difficult to detect faults at low load. With constant monitoring, you've got data 24/7, 365 days of the year. And we have a load map, a piece of patented software, which by using the thermal data and load data, we can actually predict faults at a very, very early stage. We're telling you a fault when there's maybe only a few degrees of delta reading on that joint. A thermographer, yes, they may see the temperature, but they don't correlate to load and can give you that indication. As we said, thermography is external. Constant monitoring, your sensors are inside the gear. You're at the point of interest. You're looking at the joint, at that cable connection. And it's a fit and forget. There's no maintenance. As we mentioned earlier, those windows require maintenance. Well, you want to fit a system, you can extend your maintenance cycles. Not, I have to open the gear every 2 years to change out a window, change a gasket, recalibrate the window to my camera. No, leave it closed. It's fit and forget. It's continual data. And it can be integrated into the SCADA. It's not just an image that's taken into a document, it's printed out, and it's filed on the shelf back in the office. You've got that data 24/7. And that safety is giving you those alerts that you know it's safe for the equipment. You know it's safe for personnel to work near that equipment because you know the health status of the joints. IIoT, so the Industrial Internet of Things. It's the big buzz around the whole industries, whether they're oil and gas, data center, mining, hospitals, marine, you name it. The IIoT. It's enabling systems with sensors to give us predictive maintenance. That could be temperature, its pressures, its flows, but you need the data. And it helps eliminate the risk of that equipment failing by having data. It gives you increased safety. You're improving the performance of your equipment and your processes because you're not having the downtime. So it's helping you reduce the costs and increasing the understanding of how is that equipment operating? Is it the best equipment? Isn't it the best equipment? You can start doing comparisons between breakers, switchgear. You know what's happening in your environment. So continuous thermal monitoring, really, it's the most advanced approach to assisting you as an end user, as a customer, as an operator, to reduce your downtime. So increase that uptime. You've always got those sensors on. They're providing real-time alerts. You're identifying those faults early. You're getting a very early warning. You've got an issue starting to occur in the switchgear, within a board, within a transformer. You can take action. You can plan. You can plan those actions. You can plan the maintenance. So, yes, it's truly becoming predictive. And by doing that, you're still going to have downtime, but now you've got a very, very short window of downtime while the connection is repaired, rather than you've destroyed the board, you've now got huge downtime. And it's all data driven. all that data that's been pulled in, then linked with AI, it helps you get the most advanced approach. Just a very quick run through a little case study here, and all this information is available to read on our website. You can go and actually pull this case study off. But this is with a global tech giant, not mentioning their names, we can't, but it's one of the largest tech giants in the world. And we've been installing CTM technology for, I think, now 2 years plus in all their areas. We've installed in excess of tens of thousands of sensors, and that's in multiple sites, in multiple locations all across the world. And the benefits are savings, we're preventing outages, it's improving that efficiency, it's giving data, and that's data from day one, even at commissioning stage. You've now got data that can alert you there could be a loose connection during commissioning. You can catch that. You can detect it. You can go put it right. But then you have day one data for all your equipment going forward. This is the health. This is how it was from day one. And you can see what that equipment starts to do over the time and over the years. So I'll just do a very, very quick sort of recap over what we covered, then I'll hand back over to Thomas to have a few more words. Really what we've covered today is when you get an outage, the cost of that unplanned downtime could be huge. I think as we saw from those figures earlier, the Apple, the Meta, the airline, they can be huge. It's not just the cost of the equipment, it's all the other costs. Compromised connections are problematic. And they're not just costly, they're very dangerous. So it's a big safety issue. And you want advance warning. You want warning when the issue starts, before you start having a big problem. And we've looked at the difference then between preventative, or where we started reacting, to becoming periodic, to trying to be preventative, trying to catch things, to moving now with continuous monitoring into that predictive maintenance world, using the data. Use that data to tell you what's happening. So you can follow and get highlights in your LinkedIn feeds if you follow us. You can visit our websites. You can learn how CTM improves your resilience. We've got lots of case studies and data on there. And you can connect and reach out to Thomas, to all our sales leaders, all our sales teams, any of us globally. So I'll just hand over to Thomas for a last few words, and then I think we'll dive into some questions that I can see coming in.
Exactly. Thank you very much, John, for taking us through the fundamentals and the characteristics of continuous thermal monitoring today. So we've already received a couple. Let me jump in and just start from here. John, this question is for you. It says, how many failures can be caught through predictive and preventive maintenance approaches using CTM versus conventional methods?
Okay. Yeah, actually, a good question and a good point to raise. I think looking at all the bodies, the professional bodies around, Uptime Institute and many others who've looked into this over the years, what they've come up with is sets of figures, analysed everything, and by actually using continual monitoring, and we're saying you need continual thermal monitoring, but having that monitoring in place, they actually say that we can catch up to 80% more failures than by doing absolutely nothing. So if you have no monitoring in place, you're going to have those 70, 80% plus failures. By placing monitoring in there and knowing the health of your equipment, you're going to catch 80% of those issues. Yes, you're not going to catch all of them, but a reduce of 80% is a huge amount.
It is a game changer, John. Thank you. Moving to the next question that came here. Can continuous thermal monitoring sensors be installed in small or hard to reach places? And how intrusive are they?
Yes, the sensors, they kind of missed. I mean, the sensors themselves are not large. Just thinking we're in the western side of the world, so they're about 1.25 inches in length, probably about 1/2 inch in diameter. So they're very small, they're unobtrusive, and they can be very easily installed in all switchgear. We've not come across an instant where they can't be installed. They need to be outside a minimum clearance zone for the voltage, but they're very small. So they're not causing an issue. They don't cause a type test issue. And they're non-contact. So they're not causing an issue with the equipment. The cable sensors, again, is a very small contact sensor. It simply cable ties on and is an ideal solution for a retrofit. A very, very quick retrofit solution.
Thank you, John. That's true for exotherm sensors. But let me take this opportunity, after this question was raised, to also highlight the next webinar of the exotherm webinar series around that broad continuous thermal monitoring technical landscape, the different options out there, and what's the implication for design and engineering on the one hand, but then for operations and lifetime, including retrofit on the other hand. Yeah, so stay tuned, everyone, for additional invitations to those ones. On to the next question, John. How flexible are CTM systems? Can they be scaled up or scaled down for different installations?
Oh, absolutely. I mean, yes, definitely. The exotherm system is it's a fully scalable system. We have, and I think it's actually on another one question that's just come in as well. One gateway or data card, it will accept 8 sensors. So you could have a smaller system as one little data card, 3 sensors, and that's 8. Or you could put 8 sensors, 6 sensors. It's scalable because each one is a Modbus device, and you can have multiple networks. So one network of 32 data cards, which is the standard for a Modbus serial network, you can just add more cards, more sensors. So it's very, very scalable, both up and down. You can have as small or as big as you wish.
Mm-hmm.
I think there's another one coming there that says, yeah, how many sensors can a gateway accommodate, from Brian? I think I just mentioned there that one gateway or data card, as we call them, it will accommodate 8 sensors. As far as them being rated for Class 1 Division 2 areas, I'd have to just go check on that. We'll come back on that one to you. We'll get that data for you as to which class and division it's suitable for. But they're installed in every OEM's piece of switchgear. We work with all the OEMs globally. They can all install them. There's not been an issue actually putting these sensors in that switchgear over the last 20 years that I've been here working. So we've certainly not come across any problems. I think another one that I can see, Thomas, and I don't know if you can.
Yep.
You've asked, is there an application guide for applying the sensors to specific equipment types? Yes, there is. We have guides for low voltage and medium voltage equipment, which will show where we would encourage sensors to be. And for those two, really, it's site-made connections. So where the boards are brought together on site from transport, shipping, split, line side of incomers, load side of the feeders. So it's every connection that's physically made up on site. They're the weaker areas. On transformers, we've got a very good application guide which shows where to place the sensors on the dry type transformer. Whereas it's the resin, it's those resin posts, the core that fails, not the actual connection point. It's the resin that goes. So yes, we have those on the website. If you visit, go try to download them. If you have any problems, then certainly reach out to any of the team and we can discuss it further. Anything else you found there, Thomas?
Yeah, John, here's another question that came in, quite broad one as well. It says, how accurate is the data that is produced?
Okay, I suppose it's a bit of a two-part answer for that one. All our sensors measure delta T, which will be covered in another. In fact, I think it's webinar number 3, the importance of the temperature. So we measure a delta T reading. The sensors themselves are, the infrared sensor is plus or minus 5%. Now, that sounds, oh, crikey, that's huge. But it's plus or minus 5% of the actual output reading. If it was 40 degrees C, yes, that's plus or minus 2 degrees. The same with the cable EM sensors. I think they're plus or minus 1 degree C, actually, those. But the other point to take into consideration is repeatability. The sensors are fully repeatable from today, tomorrow to next week. And we also must remember, this isn't process control. We're not looking for, have I got a temperature of 23.4 degrees delta? And 2 hours later, have I got 22.1 degrees delta? We're looking for a trend. Is there a rise? If that is out plus or minus 1 degree, really, we don't care. We're not interested in that because it's repeatable. We're seeing that trend. Now, if the alarm limit says trigger at 22, if we're at 21, or we're at 22 or 20, well, you're at that alarm point. You know you're starting to run into trouble. If we hit 40, again, is it 39? Is it 40? Is it 41? No, you're at a critical point. Whether plus or minus 1 degree is, at that point, is irrelevant. But it's an early warning. And as I said, it's 100% repeatable. So it doesn't degrade over time.
Yeah. Great. Thank you, John. Here's another question around the economical feasibility of continuous thermal monitoring versus currently followed approaches and options. You already discussed earlier that 4 out of 5 failures with this root cause can already be detected utilizing continuous thermal monitoring in operations. But let me take this and share something that we recently went through with a customer, not around the operational advantages, which are obvious, but with regards to initial investment, the CapEx piece of the solution compared to conventionally used approaches. In this specific example, the customer was looking around adding infrared viewing windows to the lineup in question. And the question was, how would continuous thermal monitoring solution compare from a cost perspective versus those viewing windows approach? Such infrared windows come with a cost over a couple of $100. Then comes the design and the engineering and the manufacturing integration of those ones. But then there's some operational costs to those ones as well. Not only do you have the costs of sending people around with the thermographers and the cameras to look through those windows, but the windows themselves are subject to maintenance. Maybe you have to replace the windows because the crystals degrade every 5 years, every 10 years or so. So long story short, the outcome of the analysis was utilizing continuous thermal monitoring for that same application, integrated in the equipment, ex-factory off the bat, came pretty much at the same cost as getting these windows procured, installed, manufactured once off the bat. So not only does CTM provide the advantages during the operations, the OPEX side, but even with regards to initial investment, it's a wash, it's a no-brainer to consider continuous thermal monitoring, 24/7 condition assessment. On to the next question here for you, John. This one is around standards. Is CTM covered by ANSI NEMA UL or IEC CE?
All our CTM products are certified. They all undergo full CE certification, so CE safety, as well as EMC, EMF, so quite a rigorous testing regime. And again, all our sensors go through UL, so it's after the CUL, so approved for Canada as well. So yeah, all our devices are approved. They don't go through any specific testing for switchgear, but I think as we've seen over the last 25, 30 years now, again, because the sensors are non-contact, they're not in contact with a bus connection, they're not in contact with anything inside the gear. There's never been a problem because the UL certified devices are placing them in equipment and having that piece of switchgear's UL file updated. So yeah, there's no specific certification for gear, but we're all CE and fully UL certified.
Very good. Thank you, John. Doing a time check, maybe we have time for one more question that came up here. Quite interesting one. It says, is there any information about reportable incidents or accidents involving conventional infrared inspections on energized equipment?
I think that the answer to that one would be yes. Then there has to be. It's not something that we've got immediately at hand at the moment that we can comment on. But yes, there has to be information out there because yes, when there's an incident as such, then it is reportable. You know, it's reportable to an OSHA, a health and safety, depending what region we're all working in. So yes, that information must be out there. At the moment, as I said, we don't have that to hand, so we'd have to go out and have a look and come up with this. I think the only information we do have is, and it's come up in another question, is obviously that neater estimate of when they went looking through and talking with insurance companies, that it was that 35 to 40% of failures were all due to physical connection failure within the equipment, so loose connections. As far as a time period, again, we'll just have to go and have a look further and pull that information together so we can respond to those once we've got the information, and then we can circulate that to the group who came and listened.
Yeah, very good. Yeah, thank you, John. Yeah? You're right. In any case, involving or running conventional infrared inspections will come along with the personal safety risk of deploying people to site, getting them prepared for the hazardous environment, getting them equipped with PPE. It's only going to catch hotspots in a snapshot of time, like you discussed, yeah, versus continuous thermal monitoring catching 4 out of 5 of such hotspots having created. And from a original investment perspective, coming back to the previous question, possibly at a wash compared to all other options. So everyone on the call, please reach out, let's engage, let's discuss and dive deep around how continuous thermal monitoring can help you and your customers or you and your operations run more resilient and safer operations. I want to thank everyone for dialing in today. Thanks for your time. Hope to speak with you soon. Be invited for the next couple of Exotherm webinar series. You'll be seeing an invitation for those ones come out. Thanks again, everyone. Have a great rest of the day and rest of the week. Thank you very much, John.
Thank you. A pleasure. Thank you, everybody.